We are now ready to start our study of momentum, impulse, conservation of momentum, and see how to solve problems utilizing these concepts. We have already looked at the work-energy theorem, and we started with sum of F is ma. And what we did is use the constant acceleration kinematic equation for acceleration. V squared minus V0 squared over 2d is constant acceleration. And then multiply that by d to get rid of that d. So we have fd equals m v squared minus v0 squared over 2. Expanding, we get 1/2 mv squared minus 1/2 mv0 squared. You recognize these as being kinetic energy terms. That's how we defined it. So this then is simply delta K. So we have the work energy theorem starting with F equals ma. Now we're going to do this again. We start with sum of F is ma. This time we'll simply express acceleration in the most basic kinematic way, delta V over t. And let's get rid of that t, like we got rid of the d previously for the work energy theorem. So multiply by delta t and we get F delta t is mv minus mv0. So for the work energy theorem, we had 1/2 mv squared, both an m and a v. And now, instead of fd, we have F delta t, and we have an mv term again, but it's just mv, not v squared, and not 1/2. So these mv terms have their own name, and the name given to them is momentum. So that is what we mean by momentum. So let's look at sum of F again. Sum of F is m dv dt. Acceleration is dv dt. Well, it's possible to consider this as the time rate of change of the quantity mv. M, of course, is often constant, but not necessarily. It might vary, for instance, with a rocket engine. Well, there we have mv, and we just learned what mv is, namely momentum. So, interesting, we've now just discovered that the sum of F is rho. ddt of mv is the rate of change of momentum. So that's a very profound result, very simple, but nevertheless far-reaching. In fact, it's how Newton expressed his second law. d rho dt equals delta F. Now I'm going to put this result back up here one more time. ddt of mv is delta F, which is d rho dt. Time rate of change momentum is the net force. It's the second law, Newton's second law in terms of momentum, which is a little more useful, a little more far-reaching. Now let's consider impulse. An impulse, the symbol is J, and it's just F delta t. Well, we just looked at F delta t. That's the change in momentum, isn't it? Yes, it is. mv minus mv0. So that just says that delta rho equals J. Change in momentum equals impulse. This is the impulse momentum theorem. Now it's very important to not confuse these two ideas. The change in momentum is impulse, but the time rate of change in momentum is force. So this is just a change, and it equals change in momentum, or force times time. The rate at which this changes, the rate at which the mass times velocity changes, is an expression of the net force. Very, very different, but they can easily be confused. Now let's consider a variable force. We have F versus t, and here's our randomized function between t1 and t2. This is the average force over the interval t1 to t2. So this area that's outside of the plot is about equal to the area that's outside of the rectangle. So they should be about the same. In any case, there is an average force that can be expressed. Now, impulse equals the force times time. So since force is varying with respect to time, we integrate from t1 to t2 of F as a function of t. And when we do that, we also get the value F average delta t. So that, of course, would just simply be the area underneath the rectangle. So there it is. This is the impulse, the area under a force-time graph. We could consider this in terms of components, recognizing that this F times time is mass times velocity terms. So in the x direction, integral of fx dt is mvx minus mvx0. We can do it for the y dimension. We can do it for the z dimension. And so there's the relationship between force times time, and impulse. So how would we define or describe the difference between momentum and kinetic energy? I mean, they both come from the second law. They both have mass and velocity. Well, historically, this has actually been a very thorny issue. I'm not going to try and resolve it so much right now. You probably already know that they reveal themselves differently. One is conserved all the time. That's momentum. Kinetic energy is only conserved sometimes. So therein is a significant difference. But let's take, for instance, kinetic energy, which gives us that work total is the change in kinetic energy, which is F dot D. So it depends on the displacement or the distance of the net force. So that's work total. F net dot D. Momentum, on the other hand, impulse is the difference in momenta, and that's F delta T. So we have F dot D and F delta T. So this momentum depends on the time of the net force. Let's take an example. 1 kilogram at 5 meters per second. The momentum mv, 5 kilogram meters per second. The kinetic energy, 1/2 mv squared, 0.5 times 25, 12.5 joules. Obviously very different. Now let's consider 0.2 kilograms. 0.2 kilograms at 25 meters per second. The momentum is, as before, 5 kilogram meters per second. Same momenta. So same momentum, the same quantity of motion I like to describe momentum as. But what about the kinetic energy? Well, it's 0.1, 1/2 m, v squared 25. Oh, it's not at all the same kinetic energy. Rather, it's 5 times the amount of kinetic energy that the first one had. So there is a significant difference in the way that the momentum and kinetic energy reveal themselves, manifest themselves. Of course, we recognize that since kinetic energy is 1/2 mv squared, it's highly dependent on the velocity or the speed. So when the speed goes up, the kinetic energy proportionately goes up very rapidly, which really means that a lot more work is required to achieve the kinetic energy, even if the quantity of motion, the mv, has not changed. Now, that's a little bit hard to reconcile and make it all make sense. But they are different types of physical quantities, both being very important, but again, revealing themselves in different ways. And just something to keep in mind that that momentum, always conserved, kinetic energy, only sometimes conserved, and they certainly are not the same thing. But Newton describes momentum as force through time, namely impulse. And kinetic energy can be thought of as force through distance. So force through distance and force through time.